Ladies and gentlemen, our EDM seminar is starting. Aaron, please go ahead.
Hello and good day, everyone. This is Aaron Goldberg. I'd like to welcome you to our event today, where we're going to talk about solving time synchronization in Windows networks. Now, we know that Windows is a core component of nearly every enterprise network worldwide. However, Windows really isn't known for keeping accurate timekeeping and accurate tracking of time, which is really essential for a lot of network and business operations. Things such as shared cloud databases, virtualized environments, and billing and transaction systems do rely heavily on accurate timestamps. And this is becoming a bigger issue in face of the growing number of virtualized environments and the fact that there are ongoing compliance and legislative requirements for accurate timestamping. Today we're going to talk about the latest technology to solve these network synchronization challenges. But before we get started on today's event, just a couple things I want to share with you that can help you get more from our event today. First is you can ask a question, make a comment, or an observation. All you have to do is type your question, comment, or observation into your Ask a Question box, which is located on your console, and hit Submit. Now, we'll get to the questions during the live Q&A at the end of our event, but the good news is if we don't get to yours live, we'll get back to you with an email response. Also, and I think this is a very important best practices for attending these events, is download a PDF copy of today's presentation. It's a great place to take notes, it's a persistent reminder, and it's also something you can share with your coworkers and peers that might have this issue and want to know more about it. And finally, we do support social networking tools. You'll see those on your console where you can tweet and share them, so it's a great chance to get a lot of information. Now, I would like to introduce our speakers today because we have two real experts. Paul Skoog is Senior Product Marketing Manager at Microsemi. He's got over 20 years' experience in engineering software and GPS position and timing industries. And Steve Ratzlaff is Director of Marketing Support Services for Grayware Automation and is focused on high-accuracy PC timing systems. And he's also been a speaker to engineers with over 35 years' experience. So I want to welcome our speakers today. And with that, I'm going to turn it over to Paul, and we can get started.
Great. Thank you very much, Aaron. Appreciate that. And I'd like to thank everybody for tuning in today, for your time. Much appreciated. What we're going to be talking about here in this first section are applications and challenges that we find in Windows time synchronization. So it's going to start kind of broad, and we're going to kind of migrate down and talk about synchronizing clocks in Windows. And then along the way, we're going to show you some performance data on how well the technology works. And we hope you find it as interesting as we do. So with that, let's go ahead and get started. Next slide, please. So just a little bit about Microsemi, kind of put it in context. Microsemi is a global provider of synchronization and semiconductor solutions. And you may not have known this, but we're the leading supplier of timing infrastructure. And I bring this up because the cesium atomic clocks and the hydrogen masers that we produce, they actually contribute to 93% of the UTC world time contributions. And so why this is important is that when it comes to UTC, that's Universal Time Coordinated. That's the underlying time structure for NTP, Network Time Protocol, as well as for Windows. And that kind of plays down into the tens of thousands of NTP servers that Microsemi has sold here. And it kind of raises the question is, well, what is everybody doing with all of this time servers and time synchronization and so forth? So I thought I'd just kind of go through a few applications and see if it kind of resonates with you. So if we can go to the next slide, please. So in this case, we're looking at the enterprise NTP time of day landscape. And, you know, kind of at the core here is accurate, secure, reliable time of day for network operations and business operations. And you sort of look around this wheel, I mean, I imagine many of you will identify with the importance of log file timestamps, right? I mean, there's a lot of servers out there that collect a lot of logs. It all gets aggregated. You want to run a network report, you know, maybe some sort of fault diagnosis forensics things. You really rely on accurate timestamps. That's probably the number one reason why people actually synchronize networks. But, you know, working your way around network security, in Windows alone, Kerberos is used for authentication. Steve's actually going to talk a little bit about that. And, you know, then we get down to real-world time values, network operations, a lot of things that probably look very familiar with you. So I just kind of pick out a couple, the legal regulatory requirements and business transaction timestamps. Let's look at those for a moment. Go to the next slide, please. So in this case, looking at some mandatory legislative timing requirements, and this may or not affect you, but there's a variety of areas where there are industry requirements to maintain a certain level of time and synchronization. And if you happen to be a government defense contractor, there's one coming up here at the end of 2017. So if you handle covered defense information, cyber incident reporting, you can see that you're going to have to be synchronizing your clocks, and not only synchronizing them, the timestamps that are generated for audit records. And Steve's actually, when he talks about Windows, he's going to talk about an aspect of auditing the time and maintaining some good audit records for just this sort of compliance. The next one, stock trading in Europe. There's a new requirement there back one slide, please. Thank you. There's a new requirement there. MiFID II. High-frequency trading folks are going to be required here in January 2018 to maintain 100 microseconds UTC. And if it's not high frequency, but if it's automated, 1 millisecond UTC. So the key takeaway here is, sure, accuracy is important, but also, since it's a legislative requirement, if, say, a connection to GPS was lost, they have to maintain that time even if they're not connected to GPS. So it brings up a notion of holdover, which is actually, if we go to the next slide, please, you can see on this slide, it's an example of a large-scale system, large-scale Windows time sync. So here was an application, 50,000 Windows-based clients across 4 data centers, 2 continents. So it's a pretty diverse setup, right? They probably put a time server in each data center, at least probably a couple for redundancy. Everything has to be synchronized. You get the idea of looking at their technical requirements, authentication and traceability. But I want to point out that bullet, second from the bottom there, max 1 millisecond for 24 hours. So that's a holdover requirement, right? So if GPS were disconnected, cable or a lightning strike on the antenna, you still have to maintain accurate time across the network. And that comes into sort of a fundamental of clocks and how clocks work. And so I'll talk to that here in a slide or two. So this is a large-scale Windows time sync that's sort of real. What about a virtual one? So if we go to the next slide, please. In this case, here's a typical problem in virtual environments I wanted to share. Got an email from an infrastructure analyst at a major corporation, and it is in VM with Windows. And the problem in a virtual environment, and Steve's going to share some data on this, it's pretty cool. The problem is that missed or delayed clock ticks generally manifest themselves in the time falling behind. Okay, and you can see here, this customer had 2 big problems. One is they had an issue that they were behind in time because they couldn't access the time server to begin with. They were getting time from the internet, and internet time can be unreliable, not secure, not accurate. There's a variety of things that make it not a particularly good source of time if time synchronization is important to you. And someone might add on here, when it comes to internet time, I saw a report recently, and internet time servers are subject to the most denial of service attacks of any servers out there apparently, because NTP uses UDP. So it's very easy to just flood a time server with all kinds of packets. And so I'll talk a little bit about denial of service resilience coming up here in a moment, but it's just kind of take note that, time from the internet may be free, but it has a cost. Nonetheless, moving on here, when we look down there at the VMware, their clocks, because they weren't synchronizing, they're falling behind 12 minutes every few hours. And you can imagine if you're trying to keep accurate log files, that's not going to work very well for you. Solution, of course, was that they brought time inside their network with some time servers to keep all the window-based operating systems and servers all synchronized. So that was a solution that worked for them real well. So if we go to the next slide, I just wanted to talk about sort of the 2 fundamental problems that we're trying to solve here. One of them is that every network element, server, you name it, it has an oscillator. And the oscillator is basically used to count off the ticks that we assign a time to. But the problem is the oscillator quality varies. Some run fast, some run slow. You may not know this, but if the temperature changes, it can speed up and slow down the oscillator. In fact, we've even seen data where The air conditioning turns on and off, and the time changes. We've even seen it to where the fan inside the server turns on and off, and the time changes. So that's the first problem in keeping accurate time, sort of a physics one, a physical one. If we go to the next slide, we kind of get to the core of the problem here that we're talking about today, and that's going to be the Windows time service. So I just wanted to illuminate for you Microsoft's position on this. So the Windows Time W32 time service, they basically say this provides loose sync. And coming from their knowledge base, there's 4 key points to understand about timekeeping, or somewhat the lack thereof in Windows, and that's the problem that we're addressing here today. So, they don't guarantee the accuracy. It's not full-featured NTP. You go down there, it's mainly for Kerberos, for authentication, and some general loose time sync for client computers. But the main point is on the last bullet, when they say that it can't reliably maintain sync to the range of 1 to 2 seconds, right? So if you're one of these organizations that are trying to keep microseconds or millisecond accuracy for log file or whatever the case may be, the Windows 32 time service wasn't built to do that. And so that, of course, brings in the solution and the problems here that we're addressing. So if we go to the next slide, please. So what do we do here? How do we go about it? So first, you take a look at the Windows synchronization hierarchy, and it's pretty straightforward. You start with a reference time source, and then the time is essentially cascaded or distributed down through the network, domain controllers, ultimately down to domain members. So how we're going to do this webinar is I'm going to speak to the reference time source aspect, and then I'm going to hand it over to Steve, and he's going to tell you about all the ways and advantages and how well it works to synchronize all the way down to the domain members and monitor them and so forth in Windows. So if we can go to the next slide, please. I'm going to talk about essentially the reference time source technology, right? So there's a reference time source on top of that hierarchy. That, of course, is going to be an NTP server. I just want to share with you some technology aspects, but I'm going to put it in the context of a product from Micro Semi. So if we can go to the next slide, please. In this case, it is going to be a new time server that we came out with just recently. It's the Sync Server S600. And you'll see through the next couple of slides, we'll talk about accuracy, security, reliability of the product in solving the application problem requirements that we reviewed just a moment ago. So if we can go to the next slide, please. On this slide, we're going to talk about kind of some fundamental clock technology things, particularly accuracy and holdover. It's a very accurate clock. It's a GPS, GNSS referenced NTP time server, and it's accurate to about 15 nanoseconds to UTC while tracking GPS. So it's extremely accurate. So sort of check the box on accuracy there. But what about accuracy during holdover, right? I mean, there are occasions when an antenna cable may get disconnected or a lightning strike, or for some reason you're not getting that connection to the satellite. You still need to keep accurate time on the network, right? That requirement does not go away. And so the standard product has about 400 microseconds of holdover for 24 hours, and then it drifts away from there. Many customers where holdover accuracy is very important will opt to put in a rubidium atomic clock. It's not very expensive, and it gives a microsecond, a millionth of a second holdover for the first 24, 3 microseconds at 3 days. So obviously that's really good, but what's really important about all of that is it buys you time to fix a problem. You can still deliver accurate time to the network, to the whole Windows network, while you're in this holdover state addressing an antenna cable issue or whatever the case may be. So we go to the next slide, please. In this case, let's talk a little bit about network timing technology, because of course we are synchronizing all the Windows clients over the network. So in this case, this particular device, it has 4 gigabit Ethernet ports. They all do NTP, and they uniquely, this is a unique attribute of this time server in the marketplace, they're all equipped with hardware time stamping. So what does that mean? Why should you care? What's the value added? And I think you'll be actually surprised in a way that the value add in a way you may not have expected. So if I kind of look at this table, I look at the center column there, the S600 NTPD. Essentially, it's the NTP daemon, but we have a hardware assist to it. So it's a combination of software-based NTP and hardware-based. So you get a good overall time accuracy, 15 microseconds. The reason why it's not perfect is because it's software-based, there's internal asymmetries that degrade the accuracy a little bit. But nonetheless, it can handle a nice load of NTP requests and has a little bit of CPU security. The thing that's really interesting, though, here is this NTP reflector. This is a brand new technology here in an enterprise NTP class time server. And the NTP is 100% hardware-based. So the accuracy, of course, matches the accuracy of the clock, 15 nanoseconds. And the thing that's kind of amusing, actually, is the server capacity is 120,000 NTP requests per second. So that's kind of like me telling you that you have a 100,000 horsepower engine in your car, right? You really don't need it because that's huge capacity. It just happens to be the capacity you can get at 1 gigabit, all right? But so what's the advantage of this? Well, the advantage actually certainly comes out in accurate timestamps, but the big advantage comes out in security. Because what we do is, I mentioned about denial of service attacks on NTP. Well, in this case, we monitor the throughput coming in on those packets. And we have user set levels where you can decide what level of throughput you want to basically alarm at. And in the event the number of packet requests exceeds your threshold, you'll get a notification. And so the beauty of this is the load may surpass your threshold, and the product can still support the load, but it's telling you, hey, we're getting more NTP activity than expected on this board. You might want to have a look, all right? And we can actually do port-by-port packet loading as well. But the nice thing about it is it brings in this monitoring, alarming aspect of looking at these UDP packets that are coming in. So if we go to the next slide, please. In this case, just sort of what it is in pictures, you have a network, packets come in, inbound, they hit the hardware, and they are just turned right around in hardware. Line speed, non-NTP traffic's dropped. We let a little bit of traffic through to the CPU, but we protect the CPU by all means so that the overall availability and operation of the clock continues on. So I promised some data. If we go to the next slide, please. What we're looking at here is essentially the clock accuracy as a function of load. And this is some pretty, frankly, if you're into clocks like we are, this is pretty cool data, actually. So if I start with the left, we're looking at the processing load level going across. Each color represents an increasing load. And we increased it from 64 NTP packets per second, in this case up to 10,000. And the accuracy of the overall clock, you can see we're looking at a scale from 0 to 100 microseconds. And it was pretty much maintained. A little bit of dispersion. The dispersion you see is because there's a software aspect, a little bit to the time stamping in combination with the hardware. But as the load went up, it maintained the spec. Oftentimes with NTP software, the load goes up, the accuracy degrades. So if we were to zoom in on this and look at the chart there on the right, this is how well the reflector works. And you can see here, the load in this case, I plotted it up to about 30,000 NTP packets per second. We zoomed in 100 times. So we're looking at 0 to 1 microsecond, and it processed 100% of the packets received, time stamped it to 15 nanoseconds UTC. It just worked perfectly. And of course, we monitor that load and alarm if it's above your threshold. So it's an interesting, very useful use of the technology in providing the service and the security aspects. So next slide, please. So wrapping up here on the reference time source part, just kind of a recap. The time server sits at the top of the hierarchy, distributed down through Windows. And what's important in that particular device is the accuracy, the reliability, and the security, right? So with hardware time stamping, it's very accurate. The oscillators that you put in can give you great holdover in the event there's a loss of GPS. And of course, security is more and more important these days, and the reflector is really well hardened. So with that, if we can go to the next slide, please. I would like to introduce Steve Ratzlaff of Graywire Automation Products, and he's going to give us a great presentation here on Windows Time Sync and monitoring.
Thanks, Paul, and thanks for that interesting information on that product. I'm going to be talking today about keeping time accurately on Windows, and just tell you a little bit about me. If you'll go to the next slide. I am Director of Marketing and Support Services for Graywire Automation Products. We've been partnering with Microsemi for many years, and we provide a time source and time synchronization solution that has been, from the beginning, focused on mission-critical environments. We started in 1995, and if you're as old as I am, you'll remember that was back when Windows NT was first introduced. And at that time, Microsoft hadn't even considered the need for a timing solution on a domain. So we introduced our product to fill that need and have been leading the pack ever since. We are installed currently on hundreds of thousands of Windows systems worldwide and are the market leader in accurate timing solutions on Windows. And on the next slide, I'll tell you a little bit about what we address. Paul has touched already on what is offered in Windows today. The Windows timing or Windows Time service exists, but its primary purpose is only to keep Kerberos authentication working correctly. It was introduced when they introduced Active Directory, and that's been the focus for Windows Time ever since. As a result, Windows has kind of gained a reputation of not being terribly good at timing, and well-deserved if that's the time source that you're using. As Paul mentioned before, it uses a top-down hierarchy for distributing time, and you'll see that in the graphic displayed there. You get your time from an outside reference time source, and then the PDC or PDC emulator will distribute that time to any other domain controllers on the network. And then domain members running Windows Time will automatically discover their nearest domain controller and synchronize with it. They call that their inbound time partner. That hierarchy is built in and is very difficult to change. So that's how Windows distributes time currently. There are some drawbacks to it. The Windows Time service is difficult to know whether it's operating correctly, and there are no built-in sanity checks to know if time has varied and you didn't want it to using a wild time from some source, and there's no built-in alerting in that environment as well. So we address that, and if we'll go to the next slide, with our own product, Domain Time. And Domain Time consists of these four components. We have a high accuracy time client, which is the piece that synchronizes time on the individual machines. Then we have a domain time server, which is a software time server that can be placed anywhere on the network you need to repeat the time. It can also be installed on domain controllers to replace the Windows Time service for distributing time in that hierarchy we looked at. Then we have a domain time manager, which is a central console that allows you to remotely install, configure, or update your machines from a single machine. And then as a plug-in to that, we have an audit server piece that provides all of the collection of historical data, synchronization records, and creating audit trails that are required by so many regulatory requirements. In addition, we provide real-time alerting using that product so that you can know right away if there are any components that are not working. That all works together as a single time system. And on the next slide, we're going to talk about the time hierarchy. If you remember the graphic on the right, the top-down hierarchy that Windows uses, we can plug into that and replace Windows Time entirely, providing much more accurate time plus all of the benefits I mentioned of auditability and reliability. Or, in many environments, use a different structure for the network. Perhaps you just have a group of work groups, or you're interacting with other machines in other hierarchies and topologies that are more complicated. Domain time is very flexible and can be adapted to fit whichever hierarchy you're used to. In addition, we use multiple time protocols. We're not limited to any particular source, so that you can work interchangeably with other devices on your network very easily. Okay, if you'll go on to the next slide. I'm going to talk a little bit about the domain time client component I mentioned. It's much more than just a simple utility to synchronize the time, and that's critical in a mission critical environment to be able to do not just synchronizing the time, but to make sure that the time is accurately synchronized. And our products are designed from the ground up to take advantage of the different characteristics on each Windows version, and it's optimized to provide the maximum accuracy in that environment. We also have designed the product to not be affected by system upgrades. Quite often with Microsoft updates, certain things can break because different DLLs have changed out. But since we don't use those, we're not affected by standard Windows updates or upgrades to new versions. In addition, we're quite a bit more efficient than the Windows Time Service, so we take less resources. And we also support physical machines and virtual machines. In fact, we have special capabilities to handle virtual environments, which I'll talk about in just a little bit. Also, Paul has talked a bit about denial of service attacks, and that is a real issue with time services. All of our time products have built-in denial of service protection, where we'll reject packets that are being sent that exceed certain thresholds that you can set. In addition, we have important fraud protection on machines so that if you have a user that's trying to change the time to fudge a time record, or if you have other programs on a machine that are trying to change the time, Domain Time will notice this, note it, and also change the time immediately back to the correct time to prevent against fraudulent time. We also support the authentication methods, both for NTP and a built-in Windows authentication, to provide protection against man-in-the-middle attacks. So it covers a lot of ground. On the next slide, another important factor, and those of you who are used to supporting software on networks know that the major cost of the software is not in the initial purchase, but in the cost of maintaining it and keeping it operating over time. And Domain Time recognizes this, and we've designed it from the ground up to be easy to install, easy to maintain, and to be manageable by the systems that you're already used to using. So, for example, you can set client parameters using Active Directory policies so that you can have clients configured for different aspects of your enterprise. Or you can use standard software packaging, such as MS-SCOM, to distribute the packages, if that's what you're used to in your environment. Or you can use our own products to remotely install and upgrade. But then in all cases, there's no need to go and touch each machine in order to configure them. In addition, we provide easy-to-use troubleshooting tools such as detailed logs, and we also provide alerting so that you can know if a machine isn't working, and also integrate with your existing network management systems using SNMP. Okay, on the next slide, I'm going to talk about our server piece, and I mentioned before that it allows you to place a time source anywhere on your network that you need it. Basically does everything the client does, but it also provides multiple time protocols. So you can synchronize your time using NTP, but distribute it via PTP, for example. In addition, since we plug into the Windows hierarchy if needed, we provide the special Microsoft proprietary NT5DS mode authentication, which is Windows authentication. In Windows domains, Windows members use this authentication. It's a shared key among all machines on the domain. So our server is able to speak that language and integrate. And at this point, I'm not aware of any other product that can do that in the Windows environment that way. We also provide additional redundancy features in the Windows environment so that if your master domain controller goes offline, the slaves will continue to synchronize with it and provide time. Or if you promote a DC to master, it will automatically become the master controller for the environment, and therefore provides you a lot of added redundancy beyond what Windows itself provides. Okay, on the next slide, I'm going to be talking about the manager and audit server pieces. I've already touched on the fact that our manager can allow you to remotely install and configure, but it also includes other tools such as the ability to monitor synchronization and raise some alerts. And it also can keep your machines updated with the current versions of domain time automatically if you'd like to do that. The audit server piece is actually a plug-in to the manager, and it adds the ability to not just monitor machines, but to audit them. And that means to collect their current synchronization history in a central location so that you can actually drill down on the machine to any particular machine and know at this particular day, at this particular time, was this machine synchronized? And if so, what were its time sources? So you can easily demonstrate to any auditor that your machines were synchronized and the provenance of the time that's on that particular machine. That's becoming increasingly important with these new regulatory requirements that are coming. On top of that, we also provide the ability to generate reports so that you can integrate that with other systems or provide that to auditors on a regular schedule, and even provide automatic failover for disaster recovery sites so that if the main system goes down, you have a backup system that automatically takes over the auditing piece. Okay, on the next slide. So this is down and answering the question that we started with. Can you actually keep accurate time on Windows? And the answer, of course, using domain time is yes. We have some suggestions for you on keeping the best possible performance on your Windows timing network. We've discussed some of these components already. Starting at the top, the reference time source needs to be accurate, reliable, and needs to be local. So that it's important that if time is important to you, you definitely need to have a hardware time device as your ultimate source of time. In addition, there are differences in how physical hardware handles timekeeping, and the more modern machines have additional timers on the motherboards that allow much more accurate timekeeping than was originally present on machines. So if time is important, we recommend you use modern hardware. In addition, and this is a part that is often overlooked, is that your network is an important component in time accuracy. Time protocols use UDP, and UDP is subject to disruption on a lot of normal networks. It can be discarded if the machines are busy, if you have routers or switches that are overloaded, or it can be queued and sent later. And since that's what time protocols use to measure accuracy, that can easily skew your time. So having a healthy network that's uncongested, that is symmetrical, in other words, a packet takes the same amount of time going to the time source as it does coming back. These are all issues that are critical for very accurate time. So you may need to consider if you're needing to meet high accuracy requirements, you may need to upgrade some of your network components to be low latency. Okay, on the next slide, we're going to get down to the nitty-gritty. Clocks are kind of like unruly children. They kind of tend to go off and do their own thing if you leave them alone. They drift, and they can jump backwards and forwards. So the process of using a time management program is, we call it clock discipline, and basically you're training the clock to be accurate. And there are several components to that. First is a term maybe you're not familiar with, synchronization. That's just a fancy word for making sure that clocks run at the same rate as the time source. In other words, 1 second advances at the same rate on all of your clocks. In addition, synchronization is the ability to precisely set the time to match your time source. So obviously for an accurate clock, you really need to have both. It needs to be able to be set properly to the correct time, but it also, once set, needs to run at the correct rate. And a lot of time programs, management programs, don't really pay much attention to training the clock rate. They might do fairly well at setting the time, but they'll let the clock continue to drift at original rates, and clearly that's not sufficient. Whereas domain time is designed to do both. It trains the time to stay well synchronized, and then also synchronizes at the maximum accuracy possible for the operating system. In addition, time can be affected by other things. And I mentioned earlier about people trying to set their time for fraudulent purposes. But quite often, other things on the machine, other processes, will also attempt to control the clock. If your time program isn't aware of this, then your time can be wrong, even though the time seems to be being synchronized. So domain time also has sophisticated capability to recognize if the time is changed by some other product, and it will automatically reset the time to match the time source and flag in the logs that you have an issue. So you'll always know that the time actually is correct. All right, on the next slide, we're going to talk here about what kind of accuracy you can actually expect to see on Windows. And first thing to remember is that all versions of Windows are not identical. This chart shows the various versions of Windows being synchronized using various network protocols. So at the bottom of the chart, we have Windows being synchronized using NTP, or our own DT2 protocol, which are both time request protocols. It asks for the time and then gets an answer back. And at the top is the PTP protocol, which is more of a time streaming protocol where time is constantly being pushed out from a time source. You can see that accuracies change there depending on the protocol and also on the operating system. The middle column, we talked a little bit already about synchronization, and that's just how well you can synchronize the clock rate to match. And the synchronization column then is how accurately you can expect the time to stay and be synchronized. And if you're looking at the latest versions of Windows, you can see that we can stay very accurate. Here we're talking about 2 microseconds of accuracy. Excursions just basically discusses what happens in operating systems when the operating system is busy doing something else other than keeping time. It can cause time to be paused or drift ahead. And you'll see different versions of Windows behave differently as well when it comes to what they're doing otherwise. So in summary, this chart, which is presuming you're on a hardware time source, on a low latency network, and on a modern physical machine, that will show the kind of accuracy you can expect. All right, on the next slide, we're going to talk now about virtual machines, because to this point we've been talking about accuracy on physical machines. So if we can proceed to the next slide. Now, I might not be seeing that advance. Oh, I'm sorry. If you'll go back, I didn't see it advance to the previous one. I'm going to talk about Windows time on VMware. And these charts are fairly typical charts of what you might see using Windows time on a virtual environment. And virtual environments are kind of like any problems you may have with your operating system always get magnified because you're sharing resources with other. So at the top, you see a graph on a domain controller, and you see it may seem to behave well for a while, but then something happens on the virtual system, and suddenly it's 350 milliseconds off, and the product doesn't notice. It just continues to drift away. That's fairly typical. And the graph below is a time member, a member server, synchronizing with the DC, and the dots, each dot represents 1 synchronization per minute. You can see here it takes almost 15 minutes for the time to even get close, and here it's at 50 milliseconds. And then once it's there, it's no longer corrected, and again, it just drifts away. So clearly, Windows time on a virtual machine is really not a workable solution. And on the next slide, we're going to talk about the differences with domain time. Things look quite a bit different. The top graph is actually a VMware machine, and here we're zoomed in on our scale even closer, showing that with NTP, it's easily staying under half a millisecond. That's 500 microseconds. Whereas using PTP, which is the bottom graph, we're staying under 10 microseconds of accuracy, and clearly that's good enough to comply with all the new timing regulations. So dramatic difference in performance using domain time. And on the next slide, things are even better on VMware. On Hyper-V, excuse me. Hyper-V, which is Microsoft's own virtualization system, In their later versions on Server 2012 and 2012 R2, have done a great job of virtualizing the clock. And so you can see the top graph is at the same resolution as the previous graphs we were looking at, and their time synchronization looks basically flat. And zooming into our maximum scale on the bottom, you can see that that virtual machine is keeping under 4 microseconds of accuracy in a virtual environment, which is really quite extraordinary. On the next page, I'm going to just summarize kind of what we've talked about. Virtual machines, keeping time on them is not trivial. There are a lot of things to keep in mind. There are a lot of variables and things moving at one time. VMs tend to share resources among machines, and every hypervisor type handles emulation differently. So any timing problems you have are going to be magnified in an operating system. And to summarize what we have experienced in our testing, Hyper-V tends to behave the best on the newer versions of Windows. The older Hyper-V on Server 2008 is not quite as good, but still fairly stable within a modern OS guest. And VMware has other challenges that aren't present in Hyper-V. It can be disciplined well, but it's subject to problems that you wouldn't necessarily see on Hyper-V. For example, VMware will occasionally synchronize its time to the host machine in a stepwise fashion, which can sometimes mean time might go backwards, which can be disastrous. And also, time can be synchronized to the host when other things occur, such as taking a time snapshot or moving machines between VMware hosts, and you may see time again be synchronized outside of what you might expect. And if your time management program isn't aware of this, then time can actually run at an incorrect rate for quite a long time. So that covers the challenges. And I'm going to give you some tips on the next slide on ways to help timing in your virtual environments. And of course, using a good time manager is important. Domain time makes it easy to comply here. But one thing you need to do in a VM is actually synchronize more often than you might on a physical machine. The drift that's inherent in VMs tends to be more present, and you need to correct for it more often. So synchronizing is important. And I also touched a little bit, but VMs are subject to things that our physical machine may not. VMs can be paused or suspended or moved to other hosts where the performance is different. So you have to have a time program that's aware of that and immediately adapts to it. In addition, you also have to have the host time synchronized well to deal with those kind of situations I mentioned where the time may suddenly be synchronized to the host. And also, since things change rapidly on VMs, a new VM may start up or a machine may come under extra load. And a machine that has been running well for days or weeks may suddenly be synchronizing poorly. So you need to have a monitoring system in place that lets you know about that and helps you deal with it when those situations occur. So that summarizes keeping time both on Windows and Windows on virtual environments. So with that, I'm going to turn this over to Paul.
Great, thanks, Steve. Steve, I think I learned something every time we talk about this. It was really good to see the data and how well it worked. So thank you for that. If we can go to the next slide, please. Just sort of wrapping up here on solving Windows time sync problems. It is pretty easy and it's very affordable. We covered essentially 3 main topics. Oops, we can back up. Thank you. The synchronization aspect, right? The monitoring, and then an auditing aspect. And so when you put it in context of that, starting with an accurate reference time source like a Think Server S600, that's going to be a good, accurate, secure, reliable time for the network. These things are easy to install, and quite frankly, you can just forget you own it oftentimes. They just work in the background, just providing NTP timestamps to the network. So when we get to the network, then we have the solution of domain time 2, which is putting essentially software servers on the domain controllers and then a software client on all the other Windows clients, replacing the Windows 32 time service with something that was purpose-built to keep accurate time, to monitor that time, and also audit that time, right? So there's a lot of advantages to the domain time 2 implementation on the Windows network. And of course, as Steve just presented, the great results of accurate timekeeping in a virtual machine. So sort of at the end of the day, really timekeeping on a network becomes something that's necessary to log file accuracy, all kinds of things. It's often taken for granted. Oftentimes, it's one of these technologies that you install, and you kind of want to forget you own it. You just want it to work in the background and have that peace of mind that the network is tightly time synchronized. And of course, we want to be notified when it's not. It's one of the big advantages of domain time 2 as well. And then if it ever gets called into question whether it was synchronized or not, then you can demonstrate proof. Okay. And so that's sort of this top to bottom advantage of going from a reference time source all the way down to synchronizing the clients, the monitoring, and the audit. So with that, I think we draw to a close. I think we can go to the next slide. I want to thank everybody for the time and attention. Aaron, I think it's back to you.
It is back to me for Q&A, for a few questions. All right, well, let me start off. And the first question I have here, Steve, this is for you. Does domain time work on mobile devices?
That actually is a good question, because mobile devices have challenges to time that a physical machine on your desk or in the server rack might not have. And obviously, one way that mobile systems are saving battery power are by changing the rate of the processors and other components of the machines. So Windows, obviously time is affected when that happens. So domain time does indeed run on any Intel-based Windows device, mobile device, and will synchronize its time and also compensate for those differences in power-saving modes.
All right. Okay. Paul, I've got a question here for you because you mentioned this a few times. Why is holdover so important? This is a question from Scott.
Yeah, it's a good question. If you think about it in context of that example I had, whether it was multiple data centers, right? And they had a timing requirement that they had to stay within a millisecond and cross the network UTC. Well, they have this distributed network, and you put time servers in each data center. If there's a problem in one, you still have the requirement for accurate time in the event, let's say the GPS signal became unavailable. And so that's why an upgraded oscillator maintains time in that holdover, which allows the network operator to address the issue, but you can still maintain that requirement of meeting the particular accuracy of all the clients in the network while you resolve the problem. And it's the holdover of like rubidium oscillators that allows you to keep that time when you're not connected to a reference source like GPS. So.
All right. Steve, I want to go back to you. And this is a question, it would seem obvious, but I know we need an answer to it, is what about time zones, leap years, leap seconds, all those little vagaries to time?
Yeah, and I tend to get that question twice a year whenever there are adjustments to time zones. Paul mentioned UTC time, or Universal Coordinated Time. Windows itself internally keeps time on UTC time. It doesn't really know or care about time zones and leap years and leap seconds. So the adjustments to that are actually done by the operating system itself based on tables that it keeps. And if you're keeping your Windows machines updated with regular updates, Microsoft keeps those tables pretty accurately. But leap seconds are kind of a special case, and if you're familiar with how that works, because the speed of the Earth rotates at different rates, it tends to speed up, or in most cases it's slowing down. Keeping the time matched with the rotation of the Earth around the Sun requires adjusting clocks to add or subtract seconds, and that happens sometimes once or twice a year. The distribution of the leap second through NTP via GPS is done with a notification that's given, so clocks know that there's going to be a change, and then they're supposed to take care of that change automatically. But different systems handle it differently. Domain time is aware of this. It schedules the time, and actually makes the time change for a leap second invisible to the applications. You may have seen some news reports last time there was a leap second where machines were affected. Suddenly there was an extra second to the day, and it changed logging and caused problems on all sorts of machines. Well, that doesn't happen on a machine running domain time because we make the leap second transition invisible to the application.
All right. And Paul, I want to go back to you. You mentioned the numerous DDoS attacks that happen on time servers. Can the S600 withstand a denial of service attack?
Well, that's a good question. The S600 is new, and it was purpose-built in anticipation of denial of service attacks being levied against the server, right? So we protect the CPU by bandwidth limiting packets to it. So just under standard operation, if it's getting hammered by NTP packets, we don't allow enough to get the CPU to cause a fault. We do packet monitoring on every port so that these can have user set levels. So if the packet load is above what expected, you can get notified. But the real robust solution is in the NTP reflector, right? Because it is doing everything in hardware and it is connected to monitoring. And so the load goes up to the full line speed of a gigabit to the server. This is the NTP denial of service UDP packet load. The hardware will service all of it, okay? Without a fault there, and assuming that the user has set some threshold for notification, as soon as that threshold is met, exceeded, even though the packets are still being served, the operator will be told that the threshold's been exceeded and you perhaps are under a denial of service attack. So I think the answer is yes, it was built to withstand a denial of service attack and let the operator know if they're being subjected to one.
All right. While we're on the security topic, Carolyn has a question for you here, Steve. There's been a lot of news recently about NTP vulnerabilities and exploits. Is domain time too secure?
Yeah, it's actually related a lot to what Paul was just talking about. NTP devices, particularly on the internet, have come under a lot of issues recently due to some design decisions that were made with NTPD, which is sort of the standard open source program for distributing NTP, particularly on Linux-based machines. And some of the utilities that were present in that package have been used to create magnification attacks, where you send a packet or two to a machine running NTP, and if it has this vulnerability, then they can send out a very much larger size attack against other sources. And so you can, with just a very few packets, create a huge storm of UDP packets directed against any particular target. Since domain time is written from the ground up, we don't use the NTP code. We don't use the libraries. Again, we are optimized to run in the Windows environment, so we don't have those same vulnerabilities in the application.
Right.
I think that was the original question. Yeah.
Yeah. Yes, that is. Paul, I got one more for you. How does the S600 compare to time from the internet?
That's a good question. I get asked that frequently, actually. It kind of comes down to three main things: accuracy, reliability, and security. Right. You have to keep in mind that that's not your clock. It's someone else's clock. They've made it available for public use. They're not guaranteeing the accuracy, much less are they guaranteeing the availability of that time. You're going out through your firewall over the public internet to retrieve timestamps, right? So if accuracy is important, you want to bring a clock inside your network because it's far more accurate to have a time server in your network than it is going out on the internet, just because the asymmetric delays in the path to and from it, and Steve actually mentioned that a little bit. Reliability is important. I think I cited an example there, and it happens frequently where, the time source became unavailable. It's someone else's clock, right? And maybe their network connection is down, and maybe decided not to make it available. Who knows? But more and more in this day and age, it's becoming the security thing, where public servers are becoming a target, frequent target, actually. I mean, you do a little Google research, and you'll find there's a lot of continuous attacks on NTP servers, which essentially creates a denial of service to you as a consumer wanting to consume that time. Well, that clock may be under attack or being loaded up artificially by people deliberately targeting it with UDP packets. So if any of those things, accuracy, reliability, security, are important in your network operations or your business operations, you're going to want to bring that time inside your firewall and pull up a product like the one I showcased here, the ThinkServer S600.
All right. Well, I really want to thank you for your time today. Steve, Paul, you guys have been great. And I want to thank MicroSemi for sponsoring today's event. Just a couple things before we go. First, download a copy of today's presentation. Again, I can't stress this enough. It's a great resource. It's something to share with your peers. Do take advantage of that. Also, we have a sub-1 minute survey. If you could provide your feedback, we take very seriously that you give us an hour of your busy day, and we want to do the best job we can with these events. Finally, within about 24 hours, we'll have a recorded version of this event, and that'll be available at www.eseminarslive.com. And while you're there, you can check out our calendar of upcoming events. With that, this is Aaron Goldberg. Have a great day, a great afternoon, and a great rest of your work week.
Ladies and gentlemen, our EDM seminar is starting. Aaron, please go ahead.
Hello and good day, everyone. This is Aaron Goldberg. I'd like to welcome you to our event today, where we're going to talk about solving time synchronization in Windows networks. Now, we know that Windows is a core component of nearly every enterprise network worldwide. However, Windows really isn't known for keeping accurate timekeeping and accurate tracking of time, which is really essential for a lot of network and business operations. Things such as shared cloud databases, virtualized environments,